Welcome to the Protecting Groups module of the Carbohydrate Chemistry stream of resources. In this module, we're going to discuss some of the most common protecting groups used in carbohydrate synthesis, including acyl groups, alkyl and silyl ethers, as well as methods for nitrogen protection. We will finish with a discussion of the concept of orthogonal protection. Let's begin with acyl protecting groups. Acetylation and benzoylation are the two most common types of acylations, with acetic anhydride, or the acyl chlorides, used to introduce the acyl group. The reaction is most often carried out in pyridine, which acts as both a solvent and a base, and dimethylaminopyridine, aka DMAP, or Lewis acid, are frequently added as catalysts. Acyl groups are removed using sodium methoxide and methanol. This procedure is sometimes referred to as Zemplane conditions. If the substrate is base sensitive, a 1:2:2 ratio of triethylamine, methanol, and water can also be used. Organotin derivatives, either stanyl ethers or stanylidine acetals, can be used to achieve selectivity in acylation reactions. Both reactions are carried out in similar ways. The organotin reagent is added first, which bridges cis diols. The acylating agent is then added, which preferentially adds to the equatorial hydroxyl group. One downside to acyl groups is that they can migrate to other alcohols or amines present in the molecule. Acetyl groups migrate more often than benzoyl groups, and transfer most quickly to groups that are cis-oriented and equatorial. Migration between hydroxyl groups is reversible, although the equilibrium lies with primary and equatorial alcohols. Migration from an alcohol to an amine is irreversible. Acyl migration is most commonly base catalyzed. The alkylation reactions described in the next section are typically carried out under basic conditions, and for this reason, it is best to carry out acylations after alkylations. We'll now move on to alkyl protecting groups, which are attached by an ether linkage as opposed to an ester. The triphenylmethyl, or trityl, group is commonly used to protect the C6 hydroxyl. It is selective for primary groups due to its size. Trityl groups are attached under basic conditions and removed through either acid hydrolysis or reduction. Benzyl groups are one of the most robust and commonly used protecting groups. Like tritylation, benzylation is carried out under basic conditions, while debenzylation is achieved using reducing conditions. Birch reduction using sodium metal in liquid ammonia is more vigorous than hydrogenation, and is useful in removing hard-to-reach benzyl groups on large oligosaccharides. Acetylysis is not used to remove these groups, as it would also cleave glycosidic linkages. Allyl groups, like the other alkyl protecting groups, are most commonly formed under basic conditions from the corresponding alkyl halide. The removal differs significantly, though, and takes place in two steps. First, the double bond is isomerized using reagents such as potassium tert butoxide or Wilkinson's catalyst, and then hydrolyzed. One-pot procedures have been developed for allyl removal that make use of palladium catalysis. Alkyl protecting groups can be added selectively using organotin reagents, just as for acyl groups. The equatorial hydroxyl of cis diols is preferentially protected. Ether linkages aren't restricted to carbon-oxygen-carbon bonds. Silyl ethers are also frequently used. Two of the most common silyl protecting groups are tert-butyl diphenylsilyl and tert-butyl dimethylsilyl, which are selective for primary alcohols due to their size. They are attached under basic conditions, just like alkyl ethers, but are removed using fluorine-containing salts or acids. The last type of protecting groups that we will look at are those used to protect amines. The amide bond, formed by typical acyl protecting groups such as acetyl groups, is extremely difficult to cleave and is only used when an acetamide is desired as the final product. A thaliamido group can be used as an alternative. When attaching this group, acetic anhydride is needed in the second step to close the ring. To revert to the amine, the thaliamido group is cleaved using hydrazine. Amines can also be converted into azides. This transformation is especially useful to avoid neighboring group participation from acetamide groups at C2 during glycosylations. Amines are converted into azides through diazotransfer, which is often copper catalyzed. Azides are easily reduced back into amines by hydrogenation, treatment with sodium borohydride, or Staudinger reduction. Now that you know how to use the different protecting groups individually, we will briefly discuss how to use them in combination. Being able to manipulate the individual alcohol groups of sugar molecules without affecting the others is an example of orthogonal protection. During the preparation of oligosaccharides, the goal is often to have a single hydroxyl group available to react and all of the others protected to avoid side reactions. When planning out a protecting group strategy, it is important to think about which protecting groups will be present for most of the synthesis and which protecting groups will need to be removed at some point to carry out additional reactions. You can then select protecting groups that will tolerate the reaction conditions at various points of the synthesis. A good retrosynthetic analysis is key. Another consideration is how the protecting groups you choose will impact glycosylation reactions, where glycosidic bonds are formed. For instance, acyl and acetamide groups at C2 actively participate in glycosylation reactions, while alkyl and azide groups do not. And so the type of linkage that you are trying to prepare will influence your choice of protecting group in these positions. One final consideration when choosing protecting groups is how they will affect the reactivity of your molecule. Using electron withdrawing acyl groups versus electron donating alkyl or silyl groups can drastically change the reactivity of a given sugar molecule during subsequent reactions. We will discuss these factors more in the glycosylation module. To summarize, you have now been introduced to some of the most common protecting groups used in carbohydrate synthesis, including acyl groups, alkyl groups, silyl groups, and amine protecting groups. We've also discussed the concept of orthogonal protecting groups. This knowledge will come in useful in the glycosylation module, where we will introduce the concept of orthogonal glycosylation and discuss the factors influencing the rate of reactions.